concept of orientation, and the idea is this. Up until now, we've dealt with some pretty, I guess what would be a straightforward approach to doing these types of problems. I've got a structure, it's got some, random set of loads on it, I cut a section. Now, up until now, I think the analysis has been pretty straightforward. In 2 dimensions, we've got 3 equations of equilibrium, sum of forces in the x direction, sum of forces in the y direction, sum of moments. So, in 2 dimensions, we've got 3 unknown components that would go inside this section. Sound good? Now, the way we've been cutting this, I think, has been pretty straightforward, just perpendicularly right through the section. What I want to do is this, okay? What happens if we make a cut that's inclined, okay? It's not perpendicular. Well, I propose that we're going to get different forces and ultimately different stresses on a section like that. Everything's going to change, okay? We're going to generate a different set of multiple stresses, and ultimately what we're going to try and determine after we go through this a little bit is what's the worst case orientation? Is it like this? Is it like that? Is it going the other way? What is the worst case orientation? Because as a designer, we need to understand what are the worst case stresses possible, because understanding that will allow us to determine, well, okay, how deep does that beam need to be? What's the appropriate diameter of that shaft and what have you? Okay, so let's deal with something simple, okay? Let's say I have a member that's being yanked on. It's being subjected to an axial load P, right? So I'm taking a bar and I'm yanking on it. Now, one of the things I want to point out are these coordinate axes. Okay, so notice I've got the x-axis going horizontally, the y-axis going vertically, right? Makes sense, right? Seems to be a pretty reasonable orientation for those axes. I propose to you that for this problem it makes sense, but in general this is a pretty arbitrary decision. In other words, I've got the axes pointed like this. What if they're pointed like that? Or pointed like that? Pointed like that? Nothing to say that we can't do that. I think what we've been doing up until now is we've been using coordinate systems that are like this because it just kind of seems to make sense, right? We've got the member going like this, the load's going like that. It seems to make sense to orient everything in that fashion. Sound good? Back to my trusty weapon, samurai sword or lightsaber. I cut a section right through this. Let's go back to some basic stats. So Austin and I are playing tug of war. He's pulling 20 pounds that way, I'm pulling 20 pounds this way, right? So since sum of forces in the x direction has to be equal to 0, whatever load I'm applying to this section, the member has to respond by developing the same internal force. Seems reasonable enough, right? Now, what we're going to do is this. Now we're cutting at an angle, okay? So I propose that if we're looking at a section like this, by cutting it at an angle, instead of developing just a single force, because we're dealing with an inclined plane, we could deal with 2 forces. I've got N representing a force normal to that plane, and then I've got V representing a shear force. Okay? Now, everything here is drawn in their positive directions, positive shear going like that on the section, and then normal force, being applied in tension. I've got those drawn in their positive directions. Remember, if I do all my math and I get a negative answer, it doesn't mean I need to develop any significant emotional problems. It just means I guessed the wrong direction, right? Okay. All right, so I've got this cut at some angle theta. Doesn't matter, just something to refer to. So if I look at, let's say, the normal force, I can take that normal force and I can split it into x and y components, right? Pretty familiar. So the normal force, I got cosine theta, sine theta. Because my angle's flipped over here, I've got the sine theta on the x direction, cosine theta on the y direction for the shear over here. Not too bad, right? Pretty straightforward. Okay. So what I'm going to do then is I'm going to collect everything together. So look here, I've got my normal force going like that. So we'll say the x component goes to the right, the y component goes up. Same thing with the shear. I'm going to look at this, I'm going to apply my trusty old equations of equilibrium. Sum of forces in the x direction has to be 0. Sum of forces in the y direction has to be 0. So far, so good? Alright, so let's look at the x direction. I've got, what do I have? I've got P going to the left. I've got what? N cosine theta that's going to the right. And I got P sine theta that's going to the left. Sound good? So I propose that, rearranging this a little bit, I've got N times the cosine of theta, subtracting that over, V times the sine of theta. Adding that up, that's got to equal P. Sound good? All right. Sum of forces in the y direction. Well, I've got two forces going up. I've got n sine theta and b cosine theta. Those are both going up. I don't have anything going down, so that's got to equal 0. So probably that means one of my guesses are wrong, okay? Because if I've got two forces going up and they have to equal 0, one of these is going to come out negative and be flipped, right? So you go through and you check it out, and you end up finding that the shear was wrong, okay? That I had the shear drawn like this, but up I got a negative answer. Again, no need to develop significant emotional problems, just means acting in the opposite direction. So plug and check, and you get n is p times the cosine, and v is negative p times the sine. Now, just to make sure that these answers make sense, we can pretty easily verify this. What happens if theta equals 0? Okay? Now keep in mind here, theta is that angle at which we cut, right? So if theta equals 0, that would indicate the perpendicular cuts we've been doing all semester, right? So let's take each of these one at a time. Okay? N equals p times the cosine of theta. What if theta was 0? What's cosine of 0? 1. So 1 times p is p, right? So that's if theta was 0. Now if theta was 0, what happens here? The sine of 0 is 0, and that would be 0, right? Which if I go back a little bit, that's exactly what we were getting right here, right? If I have a theta of 0 and I cut right through, I get n equals p, and I don't have any shear force going on at all, right? Sound good? Pretty reasonable so far, right? Okay. All right, so here's what we got so far. Any questions? Okay. Now, this is a class in mechanics of deformable bodies, and ultimately, we don't care about forces in a class like this. We care about stress, right? Now, our fundamental definition for stress is force per unit area, right? Or force over area, okay? So if I cut this section, it's got some area, we call it A0, okay? But since I've cut this section at an angle, I need the area of the area of this transverse cut. I do a little bit of trig, it's just the area of this original section divided by the cosine. So, everybody okay with that? So I can take each of these forces, I can take this force divided by its respective area, this force divided by its respective area, and so forth, to generate some definitions for stress. Okay?
Oh, because cosine drops as you increase it.
Yeah. Sound good? Okay. Now, before I start computing these stresses, I'm going to introduce a little bit of notation to you so that when you see what I compute and how I name it, I want it to make sense. Okay? So originally, what we had is a problem that looked like this. Okay? We had our x-axis drawn like that and our y-axis drawn like that. Okay? So I'm going to say that the x and y-axes are my original set of coordinates. They're my original coordinate axes. All right? Now what I have done is I've taken this and I've cut it at an angle. Okay? And by cutting it at an angle, what I'm going to do is define a new set of coordinate axes, right? And just so we're sort of clear on the naming and everything makes sense, I'm going to call this the 1, 2 axis. Make sense? All right. So the naming that I'm going to use here in a second, I want the naming to make sense. Okay? So when I write sigma sub x, I'm saying that that is normal stress along this x-axis, right? When I write sigma sub 1, that's going to be normal stress, but it's going to be along this axis. Make sense? If I write tau 1, 2, anytime we see a tau, remember that corresponds to shear stress. Okay? Now when you see the 1, 2, it's going to be perpendicular to the 1 axis and parallel to the 2 axis. So what I'm looking at is essentially this. This is my shear component, so that's going to generate shear stress, tau 1, 2. Now that should be parallel to the 2 axis. Make sense? Okay. Now for each one of these components, I want to go through and compute the stresses. So let's look at this. I've got P, right? P's acting like this, and it's acting along the x-axis, right? So I propose that the stress generated due to P is P over A, and I'm going to call that sigma sub x, because it's acting along that x-axis. Does that make sense? Okay. Now, this N generates stress. I propose it generates normal stress, but it's normal stress along this axis, this 1 axis. Make sense? So I propose that's going to be sigma sub 1. Okay? And I'm saying it's n divided by that area, which, what is that? It's that area divided by the cosine. Right? And what is n? Well, we computed that. P times the cosine. Make sense? All right? The V component also generates stress. I propose it generates shear stress. Shear over a unit area, so shear over that transverse area along that cut. That area is A naught divided by the cosine, and that shear is negative P times the sine. Yes, sir?
Why is the AT equal to A0 over cosine?
Okay. That comes from this. So if I have some face right here with some area, so let's see. Let's test my artistic. So what I'm looking at essentially is this area right here. Okay. I propose that this area is the same thing as that A sub naught that's right here. Okay. So if you want, what I'm ultimately trying to determine is what's the area of this shape right here. And an easy way of looking at that is this. Just look at this triangle, right? Here's this, some angle, right? We'll say that this side has an area of A naught, and this side has an area, oh, got ahead of myself, of AT. Make sense? Now I propose that SOHCAHTOA, right, cosine of that angle is adjacent over hypotenuse. So if I'm solving for AT, just flip, multiply that over and divide. Is that okay? These are good questions, so I want to make sure everybody's following along with this. Everybody good? Okay. Okay. All right. So everybody okay with this? All right. Enter those trig identities that you haven't seen for 4 years, right? Remember all those trig identities that you learned back in high school or maybe your first year of college? Remember, sine squared plus the cosine squared is 1. Remember all that? Tangent is sine over cosine. All those different identities you haven't seen for a while. Well, I'm going to dig some of them back up. And particularly, I'm digging a bunch of them up that are related to double angles. For instance, one of the identities I'm dealing with is that the cosine squared is 1 plus the cosine of 2 theta over 2. Okay? So notice how I'm dealing with double angle formulas. If I've got the sine squared, 1 minus the cosine of 2 theta over 2. Sine theta times cosine theta equals sine of 2 theta over 2. These are all some of those classic identities you haven't seen before. Everybody good? All right. What I'm going to do is a little bit of plug and chug. So if you see how I go from one line to another, where did you come up with that? It's all these trig identities. So our sigma sub x, that doesn't change, just P over A. But I want to look at this sigma sub 1. So this is just same thing we got here. So P times the cosine over A naught divided by the cosine. So if you're dividing by a fraction, you flip and multiply. So this is P over A times the cosine squared. Everybody okay with this? Now this P over A, that's just this. That's just our sigma sub x. Make sense? This cosine squared, I'm replacing cosine squared with that. Everybody good? All right. What about the shear? Negative P times sine divided by this. Flip and multiply. Sine times cosine. So I'm going to use this one. Sine cosine, I'm going to replace with sine of 2 theta over 2. The negative just came from there. And then the P over A, that's this. Everybody okay? All right. I want to make this following statement to make sure this makes sense. All right. If I have an element that's just subjected to a sigma sub x, that's it, just being yanked on like that. Okay? And I cut it at an angle. I propose that I generate 2 stresses, a sigma sub 1 and a tau 1, 2. And I can relate those as follows. Everybody okay with that? Sound good? All right. Now, the big thing I want to keep in mind is that was only for a single stress value. Okay? We took a single sigma sub x and transformed it into a sigma sub 1 and a tau 1 2. Okay? And I'm using that term very carefully, a transformation of stress. That's essentially what we're doing here. Transforming a stress value from one set of coordinates to another set of coordinates. That's sort of really what's going on. Everybody okay for that? All right. So far, so good. All right. So that's only for one stress, for a sigma sub x. What if we've got multiple stresses going on? Okay. So we need to discuss states of stress. In other words, situations where we've got multiple stresses going on at the same time. We've actually already dealt with stuff like this before. Let's take it. Let's go back and take beams, for example. You have a beam that's got some loads on it. You compute support reactions, right? Then you draw your shear and moment diagrams, right? So at a particular point, you can have not only some shear force, but some bending moment as well, right? That's a particular point. You can have shear stress and bending stress at the same time. Make sense? So we can have multiple stresses going on at a given location. Beams are a very common example of that. Pressure vessels are another common example of that. We're going to talk about pressure vessels later on. And any other combined loading scenario, take a member and yank on it and twist it and heat it up and shear it. Multiple stresses going on at the same time. We as engineers need to be able to assess that. Okay? Now what I propose is that if I'm looking in 2 dimensions, I have at most 4 stresses that I can see on that section. Okay? The first one is sigma sub x, going like this. Okay? Now I've got these drawn in their positive direction. So this sigma sub x, that's a normal stress, so we're talking about a tensile stress going like this, right? Also, there's a sigma sub y being yanked on it like that. Make sense? So sigma sub x and sigma sub y. Keep in mind, this is only for 2 dimensions. If we were talking about 3 dimensions, we would have a sigma sub z going like this, in and out of the screen. Make sense? 2 normal stresses, 2 shear stresses as well. So we've got tau xy, which is again parallel to the y-axis, perpendicular to the x-axis, and again equal and opposite, being drawn in that positive sign convention that we used before when we did shear and moment diagrams. Likewise, tau yx, okay, parallel to the x-axis, perpendicular to the y, drawn as follows. Everybody okay with that? Now when we draw this, typically we draw this as a single combined element, and when you do stress analysis, this is a very common convention. So there's normal stress along the x-axis, normal stress along the y-axis. That's a little typo, it should be along the y-axis. And then shear stress. Now, one of the things that might seem like, of course, another typo. I guess that's mistake number 5, right? Is that what it is? One of the things that might seem like a little bit of a mistake is that tau xy and tau xy, they're all the same. That actually is, it can easily be derived that for any state of stress, this shear stress always equals that one. If you don't believe me, I prepared a handout, and I believe I gave this to you all that one day when I loaded you all with just about every handout that there was for the rest of the semester. So I want to look at a stress element, and I want to prove to you that tau xy always equals tau yx. Okay? So here's a stress element that's dxy, or dxy, dy tall, and then dz thick. Sound good? So if I look at the area of this space, I propose it's dx times dz, the area of that face right there. This space is dy dz. Sound good? All right, so those are the areas, okay? So bear with me on that. So here's my stress block, and ultimately I'm going to use equilibrium to assess this, so I'm going to need the forces. So let's take the force in the x direction, force this way. So it's stress times area. So that F sub x, the force in this direction, is the stress times the area. And the area of that face comes from right here, just dy dz. Make sense? So it's the area in that direction, so force in that direction. F sub y, very similar. F sub y times that area, dx dz. Same thing for these shear components, txy and tyx. Sound good? Now, what I'm going to do to prove this is I'm going to sum moments. Okay? And particularly, I'm going to sum moments right there. Right there. Why am I summing moments right there? Because this component right here, this component right there, they're all going right through it, right? So I get no moment component from those normal forces at all. I mean, I'm looking at the shear components, so I should try and eliminate those as much as possible. All right. Sound good? All right. All right. So if I sum moments, let me zoom out a little bit so we can kind of see what's going on. All right. So if I sum moments, so I'm looking at the center and I'm summing moments, I can take each one of these components one at a time. So I've got TXY rotating like this, and that moment arm is dx over 2. Got another one right here going like that, dx over 2. Sound good? Same thing over here. Tau yx going like that, tau yx going like that. Moment arms are dy over 2. So sum up everything here, sum up everything here. Here's what I get, right? Now I'm going to back substitute what I had there. So, for instance, this tau yx was the stress times the area, tau xy, stress times the area. Look at these. dx, dz, dy. dx, dz, dy. Everything's multiplied. Cancel all that out, and there you go. So the shear stresses are always going to be the same. Okay? Everybody all right with that? Okay. Now, okay, so here's our state of stress. Okay, keep in mind, again, this is all based on a particular coordinate system. If I rotate that, I'm going to have a different state of stress. Sigma sub 1, sigma sub 2, tau 1, 2, along a new set of axes. Make sense? The point is to try and determine what's the worst case, what's the worst way of looking at it. Okay? We're going to see how that goes here in a second. It's all going to be based on trig, and I think you're going to find it all comes together quite nicely. Everybody okay with this? Okay. All right. Now, we derived these up here. These are the ones that we derived. Okay? And we derived those due to just sigma x. Okay? Remember, we started off with a bar that was just being yanked on. We determined its stresses, then we said, all right, here's our components. Likewise, we could go through and do the same thing for sigma y, we could do the same thing for tau xy. We don't need to do tau yx because they're equal, right? Make sense? Go through and add up all of our like components, and here's what we get, okay? We get a new sigma 1 as a function of our original stress state and whatever angle we chose. A new shear stress based on our original stress state and whatever angle we chose. Likewise for sigma sub 2. So this right here, what's on this slide, is being boxed in right there. You know, nudge, nudge, wink, wink. This might be a wise addition to a formula sheet. This is a very fundamental set of formulas. Okay? So let's make sure we understand what's going on here. Okay? So based on a given stress state and an angle, whatever orientation angle that I choose, you know, the angle from the xy axis to the new 1, 2 axis, whatever angle I choose, here's my old stress state, here's my new one. Okay? So based on a given angle, the stress states change. Make sense? All right? If you're having a hard time visualizing it, I have a little animation. So let's say you've got, you know, a given stress state. Okay? So this stress state is, you know, you input this and what have you, and you start changing the angles. Now you'll notice these lines on the sides of the square are going to start changing. So I'm going to go ahead and hit play. So you notice, here's our stress element, and as the angle is changing, notice that the magnitudes are changing as well. So this line is red because that corresponds to a negative stress. This is a negative shear stress. We've got that positive axial stress. So see what's going on as the angle changes, that stress state gets modified. Make sense? So ultimately what we're going to try and do is this. The first thing we're going to ask is, okay, given an old stress state and an angle, can we compute the new stress state? Say, okay, we can do that. What is the worst case scenario? That'll be the second step. And the third step is there a tool that we can use to make all this easier? And the answer is yes. That tool is called Moore Circle, which we're going to address later. All right. Before we break into this example, does anybody have any questions about this? This example will be pretty basic, but I just want to make sure that everything here is pretty straightforward. Everybody good? Okay. All right. Now, let's go into this a little bit. So, I have, some structure that I've analyzed. And after I've analyzed the structure, I've found the following stresses, okay? So sigma sub x is positive 6 KSI. So if you notice, in that direction, I'm yanking on it like so with a positive 6 KSI stress. Sigma sub y is negative 10 KSI, so it's in compression along that direction, okay? And tau xy is minus 5 KSI. So think, I've got some beam that's being yanked on, it's being twisted, it's being pulled in this direction, being switched, what have you. I go through and do all the stress analysis, and I get this. Now, I've calculated this based on an XY coordinate system, maybe looking something like that. My question is, what happens if I rotate my coordinate system? What are my new stresses? Okay, so I'm rotating it as follows, on a 3, 4, 5 trajectory. Everybody okay with that? Any questions? All right. Let's go into this real quick. I think you're going to find this is pretty straightforward and it's pretty plug and chug. Okay. All right. So you open up my little notebook. You believe we've done 67 pages of this stuff? So yes. All right. So there's example 27. All right. So okay. All right. So we were given a stress state of positive 6 KSI. Sigma sub y is minus 10 KSI, and tau xy is minus 5 KSI. The nice thing about a lot of this is that the units, they don't really matter a whole lot with these analyses because what you're doing is transforming from KSI to KSI, or megapascals to megapascals. Really doesn't matter. I could just say it's a stress of 6. Everything would be the same. Okay. So the first thing that we're going to do is this. All right, so let's get back to this. So the first thing we're going to do is find the angle of rotation. Now this is a 3, 4, 5 triangle, so you could argue, well, I don't really need it because I know what the cosine and the sine are. It's just the 3/5 and the 4/5. But ultimately, we're going to be taking the cosine of 2 theta and the sine of 2 theta. So I'm going to go ahead and just determine the angle directly. So I've got an orientation that looks something like this. Here's this. Got that and that. And this is 4 and that's 3. And ultimately, what I'm trying to find is that angle right there. Okay? Everybody all right with that? Okay. So I'm just going to go back to the basic trig, and I propose that the tangent of that angle is 4/3. Sound good? Opposite over adjacent. Sakatoa. or theta is the inverse tangent of 4/3. Nobody's making us do math. Somebody help me out. What do we got?
53.13.
53.13. There we go. All right. So that's theta. Okay. Now what I'm going to go ahead and do is just calculate 2 theta, which comes out to be 106.26. Everybody okay with that? All right. From here on in, it's plug and chug. All right. So we were given a stress state based on the x and y axes. We now know the angle of rotation for our new axes, the 1, 2 axes. So sigma sub 1 is, and it's plug and chug. So sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times the cosine 2 theta plus tau xy times the sine of 2 theta. Again, it's our same trig definitions that we derived before, and from here on out, it's plug and chug. So, since everything's going to consistent units, it's KSI to KSI, I'm going to leave that off for brevity. So we've got sigma x plus sigma y over 2, so that's going to be 6 minus 10 over 2 plus, what do we have? Sigma x minus sigma y, so that's going to be 6 plus 10 over 2. Does everybody see why I did that? Because remember, sigma y is negative, right? So negative 10 KSI. So if I had sigma x plus sigma y, it's going to be 6 minus 10. Everybody okay with that? Times the cosine of 106.26 degrees plus minus 5 sine 106.26 degrees. So, somebody help me out. We're going to get somebody else. Somebody over here. Somebody got an answer for me?
Maybe.
Maybe.
I think it's 7.43, I'm not sure.
7.43.
Maybe.
Okay. I got something a little different.
Yeah.
Maybe it's 3.4.
All right. Hold on. Let's take this one at a time.
I think I can ranch though, so.
All right. So 6 minus 10 over 2, that's negative 4 over 2, so this is minus 2.
That's what I got there.
Plus 6 plus 10. 6 plus 10 is 16 over 2, so that's 8 cosine 106.26 degrees. Make sure your calculators are in degree mode. Minus 5 sine 106.26 degrees.
Negative 9.039.
Okay, all right, hold on. Say that again.
Negative 9.039.
Okay, negative 9, we'll say 9.04.
Sounds good.
Everybody else get that?
Yep.
There we go. All right, negative 9.04 KSI. Everybody okay on that?
Yep.
All right, let's do the next one. All right, so sigma 2 is, now the formula is very similar, and there's just a couple sign changes. So this is sigma x minus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine of 2 theta. Okay, we'll take our time with this. So, this one right here, so we've got sigma x minus sigma y over 2, so 6 minus negative 10, so that's 6 plus 10.
-2.
Well, no, this plus.
This is plus.
Yeah. Again, the formulas are very similar. Yes, sir?
The formulas in the slide, you have
It has plus.
Yeah.
you have x plus y.
Do I have another typo?
I'm just doing what the formula says.
Actually, wait. That is right. I'm sorry. I think that is right. Let me see. Yeah. Sorry about that.
Number 6.
All right. Minus 6, that's plus 10, over 2, times cosine 106.26. And then minus, well, I'll tell you what, no. Minus -5. Maybe I'm taking too many shortcuts. Sine of 106.26. All right, let's see what we get here.
5.0.
There we go. Yes, that's right. It's 5.0 what? 5.04. I'm getting close to those 7 mistakes today, aren't I? Is that what it is? Getting close. Although, how many times did I say I had 4?
You said that like 6 times.
3 times. I'm running out. All right. Everybody got this? All right. Now, the shear one should be a little easier. All right. Everybody okay with this? Okay. So, does anybody need to write any more of this? I got that? Okay. So, tau 1, 2 equals, okay. This is negative sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. Now, is that one right? That one's right. Okay. All right. We're going to take our time with this. Negative. All right. So 6 minus -10 over 2 times sine of 2 theta, which is that 106.26 degrees, and then plus tau xy was -5. That's cosine 106.26 degrees. All right. So let's follow this out. So 6 plus 10 is 16 over 2 is 8, so that's -8 sine of 106.26 minus 5 cosine 106.26. So what does that come out to be?
It might be -6.28.
Do I have a second on that?
Yeah.
All right.
Wait, I thought you were doing sine 2 theta.
Isn't but that is 2 theta, right? Hold on, let me get back. Remember, theta came out to be 53. Yeah, no, I can understand. That's why I went ahead and did this, just to sort of have the number on the side. I didn't want to have to do that multiplication over and over again. All right, everybody okay with this? Okay, so let's make sure we understand what this means, okay? So, I want everybody to understand this. All right. Okay, so we started out with the following stress block. Okay, so we started out with this, what was that? That was 6, because that's sigma sub x, right? And I'm going to put stresses in KSI, just to sort of leave the units off. So, we started out with a sigma sub x that's 6 along that direction, right? And then we have sigma sub y, which is 10. And why do I have it drawn like this? Because it's negative. And if it's negative, it's in compression, right? Now my shear stresses, I've got drawn, let's see, that. And these are 5. I've got them drawn in the opposite direction. One of the interesting things about shear stress that you're going to see here in a second is that the signs don't really matter. Whether or not it's positive 5 or negative 5, it doesn't really matter. And it's all because of the nature of the math, particularly when it comes to Mohr circles. We're going to find later on that maximum stress, or maximum shear stress, is equal to the radius of that circle. The radius doesn't matter what way it's facing. So we'll see that here in a second. All right. Now, what I have done is I have taken this stress block and I have rotated it something like this. Okay? And I've rotated it to where that is a 3-4. Okay? Now by rotating it, I've generated a new set of stresses. So this is 9.04. This is 9.04. This is 5.04. 5.04. Does everybody understand that? Or kind of see where I'm getting at? Right? And then we've got, let's see, that came out to negative, so that's going to look something like that. And that came out to be 6.28. Does that make sense? Everybody okay with that? All right, and again, if that's still a little a little difficult to see, again, it goes back to this. Remember, as I rotate that stress block and I look at a different rotation, those stresses are changing, right? Make sense? Now, this is all trig, right? This is all trig functions. So, if I go and I plot that out, I get something that looks like this, okay? Now, this is looking at those examples. Now, these are the stresses you get depending upon the angle of rotation. Now, we started off with an angle of 0 degrees, okay? Now, this is my, if you want to think of it, my x-axis stress, or sigma 1. This is y-axis, or sigma 2. This is the shear stress. Okay. Let's start off at the very beginning. Okay. What is my x-axis stress? It's this value right there. And what is that? I don't know, it's maybe positive 6 KSI. Everybody see that? What about sigma sub y? Well, that's kind of that value right there, right? Maybe that's what? Minus 10. And this is our shear stress, minus 5, right? Now, as we rotated, okay, the stress has changed. Now I want to look right here. This is a slope ratio of 3 to 4. Okay? So let's look at this. Okay? First off, what angle is this? Okay, where does this vertical line occur? Where does that vertical line occur? Well, this is 0 degrees. That's 40 degrees. Where do you think that is?
No.
53.
Maybe 53.13 degrees? Maybe something like that? Make sense? So that's where that line occurred because that's the 3-4 slope ratio. And what are the new values that we're getting at this location? What are the new values that we're getting? Well, we're getting a sigma sub 1, that's about right there. Isn't it, right? Well, what'd that come out to be? Oh, well, I don't know, about negative 9.04. All right, what did sigma sub 2 come out to be? Came out right about there. What was that? 5.04. What about that shear stress? About right there, negative 6.28. Kind of crazy, isn't it, right? Again, it's just trig, you know? Nothing special, right? You all are masters at trig, right? You are experts at all this stuff. Okay. Makes sense. All right. So this is what it looks like if you break out Excel or break out your graphing calculator or what have you. And based on that stress state, just plot it out. As the angle changes, what are the stresses? Not too bad, right? Now, what I want to look at is this. What's going on right there? This is the same plot, but I want to look right here. There's some really interesting stuff going on at this angle. Okay? What is the shear stress right there? 0. Here's our shear stress. No shear stress. No shear stress at all. What else can you tell me about that point?
The other two stresses are maximized.
There you go. The other two stresses are maximums. Does everybody see that? It's a little tough to see, but if you go to this video, which by the way, that little animation, if you want to find it, it's on YouTube right there. But that animation is just, it's just this. But if you pay attention to this, okay, so just, I'm going to pause it for a second. So these flat green lines here and here, those are the shear stresses. And if you pay attention, as it rotates, you're going to see them get smaller. And right at that moment that they turn 0, these two lines here and here, which are the normal stresses, are going to be in their longest direction. So let's see if we can see it. Here you can see they're starting to get a little smaller, get a little smaller, get a little smaller, and bam. You can see these values, the sigma x and sigma y, are pretty large. From here on, they're just going to decrease or get smaller in magnitude. See how they're starting to go down? But at that one magic point, it's about right there. That's about as large as they got. I'm trying to get a quick draw on it or something. All right. Does that make sense? There is a magic location or what we call a principal orientation where we're getting the maximum stresses possible. Now, as engineers responsible for designing these beams, these shafts, these engines, what have you, that's what we care about, okay? In other words, we drew our coordinate system originally because it was convenient. You know, P over A, that's simple. You know, T over J, that's simple. We developed a coordinate system that made sense, but it was arbitrary. We just said, okay, the x-axis goes that way because it made our math easier. But what we really care about is that worst-case scenario. In other words, the principal orientation. All right? Make sense? Okay. So, I want to go back to this. So there is a worst-case scenario. Now, as Mr. Hayden pointed out, these are maximums, or extreme locations. Now, let's go back to that math background. How do we determine maximum locations on curves? Oh, we got to break out the C word, a little bit of calculus. Oh, no. You're exactly correct. Okay. What we're observing, this particular phenomenon where the shear stress is 0 and the normal stresses are maximum, these are what are called principal stresses. These are the ones that engineers are really going to care about. Okay? This is where shear stress is 0 and normal stress is maximized. Okay? Now, how do we determine those values? We break out the C word, a little bit of calculus. Okay? So what I do is I take one of these. It doesn't matter if I do sigma 1 or sigma 2. Let's just do sigma 1. It doesn't matter. And I want to determine the location where sigma 1 is maximized. Okay? So I take the derivative and I set it equal to 0, right? Let's go through this. So I'm taking the derivative with respect to the angle because I'm trying to determine what that angle is. So take the derivative. So if I'm taking the derivative with respect to the angle, this is all constant, right? This term is 0. Okay? Take the derivative of this. Now, technically, take the derivative, I've got a 2 sticking out here, and I've got a 2 sticking out here as well. But since I'm setting it equal to 0, I can just sort of divide all that out. It doesn't really affect anything. Now, I go through, set it equal to 0, I solve. Now, check this out. So, I've got a term that's got a sine, a term that's got a cosine. What was sine over cosine? What was that, maybe the tangent? All right. So I've got the tangent of 2 times this angle, which I'm calling theta sub p. Okay, and I'm calling that theta sub p because I'm saying that's the principal orientation. How do I determine theta? Well, I take the inverse tangent, divide by 2. Sound good? All right. Based on that principal orientation, what do I then do? How do I determine the maximum? Well, it goes back to calculus. Take the derivative, set it equal to 0, solve for the angle. Then I take that angle and I plug it back in. Okay? So I plug it back in, run it out, plug and chug, and I get this. Here's sigma, and I'm calling them sigma sub capital 1, sigma sub capital 2. These are the principal stresses due to this stress state. These are the largest possible normal stresses that you can get. I'm calling it sigma sub capital 1, sigma sub capital 2. What we're going to find is that this is a very nifty formula here in a second. This is basically the center plus and minus the radius of Moore's circle, but we probably won't get into that until next time. Everybody okay with this? Any questions? Okay. All right. Let's see. We might have time for this. Yeah, I think we can knock this out real quick. Okay. So I want to go back to that same stress state we were looking at earlier, and I want to determine the principal stresses, worst case stresses, okay? So worst case normal stresses, and then what the heck is that angle? All right? So. Okay. All right. So. All right, so we got that same stress state, the same stress state from the previous problem. Now what I want to know is what's the principal orientation, what's the principal stresses. Let's deal with the orientation first. So, all right, so what do we have? We have theta sub p, principal orientation, is 1/2 inverse tangent of a fraction. We've got sigma x minus sigma y on the bottom, 2 tau xy on the top. So, 1/2 inverse tangent. Oh, you know what? Let me throw brackets in here. Alright, on the bottom, we've got sigma x minus sigma y, so 6 plus 10. And then on the top, 2 times negative 5. So we're clear on that. That's going to be 1/2 times inverse tangent of, what is that, minus 10 over 16. So what do we got? Negative, what's, but basically it's like 16.002 something. No, like 003, like that. Yeah. So, actually for this instance, the worst case rotation is rotating it back a little bit. But if you want, you could add 180 degrees to that and say, well, I'll just flip it the other way. In the end, it's all the same. I mean, think about it like this. This is trig. We're talking about rotation. So after a while, the rotations repeat. You know what I mean? If I take an element and I rotate it, 180 degrees, well, it's right back to where it was. Okay. Does that make sense? You think, well, isn't it 360? No, because we're dealing with 2 thetas. All right. So 180. All right. So you could say, or theta p equals 163.997, and that's just from adding 180. And you can add 360, you can change it either, so whatever works. Again, we're dealing with 2 theta, so we only have to add the 180, not the 360. Okay, sound good? All right, let's knock out these principal stresses, and I think we can call them. Okay, so we'll do sigma sub I and sigma sub double I. All right, so sigma sub I. Sigma x plus sigma y over 2 plus the square root of sigma x minus sigma y squared over 2 plus tau xy squared. I'd argue that of all the formulas that engineers remember when it comes to this, it's these formulas, because these are the ones that relate directly to Moore's circle. And we'll see that on Thursday. Okay, so plug and chug. So we got 6 minus 10 over 2 plus the square root of, what is that? 6 plus 10 over 2 squared plus minus 5 squared. All right, what'd you say?
Square root of 89.
Square root of 89. Okay, all right. Let's do this, and there's a reason why. Let's start off equals, so what is this? 6 minus 10, that's what? Negative 4 over 2, this is negative 2. Plus, and then you said what, the square root of 89?
Yeah.
So let's see, that's 25 plus 864, yeah, square root of 89. So what does that come out to be numerically? No, just the square root part. I want to do just the square root part.
So 9.49434.
Let's say it again.
9.434.
9.434. Okay, so this part right here is 9.434, and this part right here is minus 2. Everybody okay with that? There's a reason why I wanted to compute it like that. So sigma 1 is, was that 7.434? I guess for units we ought to say KSI. Sound good? All right, now that's sigma sub 1. So I guess maybe we'll do this, put an answer. All right. Here's why I wanted to compute it separately like this. If you do sigma sub 2, the difference is just that plus or minus, okay? Sigma x plus sigma y over 2 minus the square root of sigma x minus sigma y. Bless you. Thank you. Over 2 squared plus tau xy squared. So see, look what happened. It's the same formula, only this went from a plus to a minus. So it's just going to be minus 2 minus 9.434. So I'm just trying to reduce the amount of button crunching on the calculator. So plug and chug, and you're going to get sigma sub 2 is minus 11.434. Now think about this, all right? What were sigma x and sigma y originally? What was it, 6 and minus 10? But those aren't the worst values. The worst values are 7.4 and minus 11.4. So as the designer, these are the ones that you care about, not the 6 and the 10. Does that make sense? Okay. Now, what we've done today is gone through, given a stress state, how do we determine new stress values and then worst cases. Next time what we're going to learn is there's a lot of trig hopping around here. And if I go back to what I learned in trig, I seem to remember the following relationship. I seem to remember that sines and cosines were really just the x and y coordinates on the unit circle, right? Remember that? So if I do a little bit of maneuvering, maybe I can represent this using a graphical technique. That'll make my life a lot easier. Hence the introduction of more circling. So next time what we're going to do is we're going to take a lot of these concepts that we did today and simplify it a little bit by using more circling. You're going to find a lot of the values that we computed are all going to be located on this circle. A lot of the principal stresses, the different orientations, it's all going to be right there in one big chunk. We needed this sort of as our background. Put this up next time. All right, that's all I got for you all today. Go out and vote. We'll see you all on Thursday.